yesterday before I came here, I was around with my boys. They are 8 and 10, and they said, "Hey, Dad, let's go play some soccer." And I looked outside our terrace, and it was wet. I said, "Hey, it's raining." But then he said, "No, it's not raining." And I was looking at, indeed, there was no cloud, right? So this is kind of a metaphor how we oftentimes in machine learning or analytics deal with causality. We take some indicators and take the umbrella to prevent from something which is not there. So that's just a little inspiration, but I would like to unfold the whole topic a little bit and tell you what we need to find causes and why it's important. So causal AI is not new, but it is growing very much so. It is a hot topic at the World Economic Forum, and also it is now in the Gartner hype cycle very much, and the National Scientific Fund of the US now funded $5 million for a research project to optimize political decision making with causal AI. So it's a hot topic, and also I will talk about the link to generative AI as I close today. But what is the problem? And there's one problem which kicked off the interest of the public, which is discrimination, and there are, for instance, machine learning algorithms that predict fraud, for instance, to loans or to some substitutions, and they predict typically, and there are lots of those buzz around that those machine learning mechanisms are oftentimes discriminating. Right? They basically just find people of a certain ethnicity to be fraudful, but actually turns out that this is not causal. So all popes are human, but not all human are popes, and that's why it's kind of discriminating. And we have this kind of discrimination also in marketing and sales or in business application, and this is one where we predict, machine learning algorithms predict whether or not someone should get a loan, right? And what you see in those prediction models is that they use ethnicity or zip code to predict loan acceptance, although it turns out they are neither causal nor needed to predict that well. There's a reason. The reason is that machine learning is not optimized to use causally true information, and all the problem comes from, or not all, but a key problem for that matter here is that this is how the data looks like. So if you take, especially in marketing, but many other fields, if you take data, it all correlates, right? It all correlates, and because it's correlating, it is, well, you can kind of use any variable to predict the outcome because everything is correlating. So, and the machine learning algorithms, they are optimized only to fit the outcome, right? It doesn't care of whether or not the information is causal for that. And but there are more things we need to fix in machine learning to get causal insights. The first we need to fix is that to understand the interdependence, because things are correlating because they are causally connected, right? It's not, we cannot fix it by running a principal component analysis on it to eliminate correlation. We need to get deeper and get and understood and model correctly the causal links between the data. But we need to fix more problems. I will talk about all those 5 topics, which is find causal directions. Yeah, is A influence B or BA? We need to measure total effects, not just direct effects, which machine learning does, only measuring direct effects. We need to be very well manage confounding variables, confounding causes. And lastly, we should care and find unknown functional properties like nonlinearities and interactions. So let's dive into each of the topics. Before I do that, when I talk about causal AI is not just one algorithm. Yeah? It is basically, it's a framework and even just a goal, right? There are different methods to retrieve causal conclusions. And when you read somewhere about causal AI, it's typically referring to the Perl framework. Yeah? And there is a software around causal lens, which is most funded with 50 million. Geminos, Bayesian, which is quite old, an open source package. But everything started, causal analysis started in, in the 70s with structural equation modeling and econometric models. They also wanted to build causal relationships, and there everything started. But there are more. There are, like from the company Explain, algorithms that very much focus on the confounder topic, or methods which build on the Granger predictive AI. So I'm the founder of Success Drivers, and we invented the software Newsrow and the universal structure modeling framework. And we actually try to kind of merge everything together. But it turns out that each of the different methodologic approaches are useful for different applications, right? In medicine, kind of there's the confounder topic, very, very important, and so forth. So depending on the topic, other methods are more useful. So we're working in marketing and sales, and we believe we need to merge those 5 topics which I talk about today and handle them properly. So again, these are the 5. First, understand interdependence of the variables, and you can. There are some methods around to handle these interdependence and the multicollinearity. And one is very old, which is not even machine learning, which is the structural equation modeling approach, which basically uses latent variables and the structure model. And by basically adjusting the definition of the latents, the measurement models, by adjusting that, it can reduce, and it reduces the multicollinearity and can kind of get a hands around that. That are early tries to handle that topic. The Perl framework approach is mainly using the so-called double machine learning approach. I will not go into the details here, but just giving you some ideas that there are different approaches to handle that. And one that we are using in our software is automatic relevance detection. And this has this used in a framework to really regulate causally an artificial neural network. So give you some examples how useful it is to apply and to get a hand on those multicollinearities in practical life. When you, for instance, look at the reason why people buy a lottery ticket, right? And if you ask domain experts, they say, hey, you know what? Old people buy lottery tickets. That's our market because we did the research. We know old people, I don't know, 80% of people who buy lotteries are old. So, but now if you collect a holistic data set and do a causal analysis, you suddenly find that the opposite is true. The older people, the less likely they are to adopt lottery playing. The descriptive fact is still true, right? Old people play lottery, but for a very different reason. The reason is that it takes time to habitualize, and the more you are experienced winning, the more you stick to it and stay loyal. So, but the recommendation and what you do as management is the total opposite. Your target group are the young people. You need to get them ritualized and get some excitement. Yeah? Correlation is not causation. And we see it all the time. Just recently, last month, we did a model on why people are donating. And they told me, yeah, our donators are so old. Yeah? Only old people are donating. So again, same procedure, yeah? Same procedure, measuring anything, and we talk about a bit how to approach that. And turns out that age has no causal impact on donating. There is a reason why people donate. If they have saved something, if they have some level of wealth, yeah, plus some attitudes, whatever, plus exposition with marketing, but still that's the key. You have saved something and then you are the target group. Again, totally different recommendation if you really understood the cause of your domain, right? And for that you need to handle the collinearities. So in this sense, I produced this very nice picture. In this sense, oftentimes purely running machine learning, you can do, I don't know if you're familiar with random forest or so, you can run machine learning on it and do a explainable AI layer, but you run the risk of not handling those collinearities properly. So at the end, it's lipstick on a pig. Next topic, finding causal directions. So, of course, yeah, the big question is how can the algorithm know whether satisfaction causes loyalty or loyalty causes satisfaction? And first off, there are some analytic approaches to get closer to that, right? One which is basically built in those Bayesian network models is a so-called PC algorithm. It's also referred as a conditional independence test. But basically it's kind of a triangulation looking at correlations. So for instance, here you see A correlates with C and B correlates with C. And B and C does not correlate. And this picture, you can basically conclude that this is a causal direction. Why? Because if the causal direction would be the other way around, information would, for instance, flow from B to A, and A and B would correlate. Right? If the errors would be, at least one error would be different, A and B would be correlating. So, and from this picture you can conclude, that's the direction, right? And little disclaimer, of course, in these examples, it's clear, but reality is always gray, and the more variables you have, and the more in-between correlations, the harder it is to really conclude it from data. But there are other approaches like that. So if you add another assumption, the assumption of additive noise. So basically The assumption that what you're predicting, the residual is added. It's always the same, has always the same variance, right? If you assume that, you could conclude from causal direction. And what you see here is, for instance, is the same data but twisted around. Yeah. So left is x causes y, and the right is y causes x. It's the same data. And if you put a regression into that, it's the same R square, totally same. Just believe me, I just did it myself, right? Because doesn't look like that, right? But it's really the same R square. But obviously, the noise is different here. Here the noise is always the same variance, but there it's not the same. Yeah? I don't know, from statistics we know that it's called heteroscedasticity, right? And from that you can conclude, assuming the assumption additive noise, that the left one is a cause, x cause y and not y cause x. So there are some of those algorithms around, but again, they are not perfect, especially when the models become bigger. And we'll talk in a few minutes, it's important to have bigger models. And that's why it's basically an imperative to start with your prior knowledge. But not start with prior knowledge in a classical sense. The classical sense would be, hey, I collect hypotheses, take only those hypotheses I know, there's theory, there's studies around that, and I only allow those to put in the model. That's conformative approach. With that approach, you cannot discover anything. You just validate your theories, right? But we want to learn something. But still, you can use prior knowledge in soft sense. Prior knowledge is, for instance, what variables you take, and what we see typically in marketing, that you oftentimes know a lot of what's cause and what's not a cause. For instance, sales, yeah, it's typically kind of an outcome, right? It's not a cause, right? It's an outcome. Or a gender or age, that's not an outcome, right? Right. So, and a brand is kind of an outcome, but it's driving sales, so it's kind of a mediator. Or if I decide to run a campaign, it's an action, right? So this decision I have made is not a cause of anything, it's basically my willpower, right? I can even experiment, yeah? An experimental stimulus is the action. So for a lot of variables we have, basically any kind of variables I can put in one of those buckets, and they have a natural structure, right? So and we can start with this framework. We should start with such a framework where we use the knowledge we have and then inform the model. And if I'm still unsure about certain causal directions, you can use the algorithms I have shown you. So that said, what's first, fish or water? Sometimes not easy to say, but that's how it is, right? So we are not in the business of finding the ultimate truth, although we want that. We are in the business of making the best decision we can with the information at hand and lower the risk of failure. And with that, we should use our prior knowledge, but not in a sense to include wrong assumptions, but in a sense to help the algorithms to find valuable insights. Third, important, measure total effects. Yeah, because causal effects are oftentimes indirect. And here an example. It has become more important even in marketing mix modeling. Marketing mix modeling has been developed, yeah, many decades ago. I think even Unilever did it 1919 first time, right? So and it was basically, I have some marketing channels, yeah, TV, print, whatever, and I have outcomes, sales, right? It's an input-output idea. But today, in the interconnected media world, we have these kind of broadcast media, but then you have media which is influenced by them. So if you are running, and that's a real example, if you're running a TV ad, people on their second screen, they start Google for this product because of or around the topic, and then they will have those ads. They will click in the ads and they will visit the shop. And if you take this information, your machine learning or your marketing mix modeling, they just focus on the direct effects of those horizontal lines, right? So they will totally disregard the impact of TV, because TV is a cause, right? People go to the ads. It's maybe different in each application, but this is a real story where we found that TV was totally underestimated. So marketing mix modeling is a causal question per se, right? And the more the variables and the channels you are using are interconnected, interrelated, you really need to think causal. Here's another example, which actually my favorite example, because it shows the power of looking after causal insights. It's about T-Mobile USA, who changed their positioning around 10 years ago, and they changed everything. Yeah, the marking, they put iPhones on top. They had introduced a flat fee, which was new. They eliminated contract terms, which was a revolution, and people loved it. But the company didn't know why. What of those things they did was a reason for their success, and that was so important because each of those moves were easily to be copied, right? Competition can copy it. Anyway, so we took their total brand tracking data, which were a lot of different variables, and found that none of those things they did were the direct cause. The direct cause for their success was the Robin Hood positioning, the perception that someone is fighting against AT&T and is the Robin Hood of the industry. And the things they did were the reason for this positioning. And this causal AI exercise gave an aha moment. They said, we need to introduce all those reason whys. We need to invent new reason whys. And that's what they called Ancaria moves. So they introduced global roaming and all those little things that again and again basically reassured this positioning. Yeah? And the success is well known, sevenfold market evaluation, record profits. The whole company, Deutsche Telekom, was number 7 worldwide, and because of that strategy fostered by causal insight, it's now the number 1 in the world. And that by causal modeling and really interested in indirect effects. Yeah? So looking for root causes, it's typically an indirect exercise. It's like the sound unfolding in the room. It's typically indirect. And if you really want to understand the impact of something, of an action, you of course need to model not only direct but also indirect causes. Cool. Next, manage confounders. That's important. So, do you know model drift? I think we are a conference of data scientists and analytics experts. You probably know that very well. You build a model and a month or a year later it's not working anymore, right? There's a simple reason. The model is not causal. Yeah, something which is not in the model has changed so that the model is not predicting the outcome anymore. Give you an example. If you real data, right? If you look at the duration of study for students and you have the entry income they get after studying, there's a positive correlation. Right? The longer they study, the more they earn. Totally unbelievable, right? Typically, the smart guys, they don't take a lot of time to study, right? Yeah, and this correlation is due to a confounder, something which is not seen in this data. It's basically the type of study. If people are having a PhD study, yeah, for instance, if they do chemistry, half of them do a PhD. And with that PhD, they earn more as an income, right? So, and because of that, if you look per type of study, duration correlates negative with income, right? So, if you include those confounder type of study, you get a causally true insight that duration of study is negatively impacting the income. If you do not have the confounder in the model, you get totally causally not reliable insights. To just give you a real marketing example, we had here, for instance, the NPS, yeah, and the churn rate. And NPS and churn rate were, in this example, were positively correlated. The better the NPS, the more churn we had per person. Yeah, which is also not plausible at all. But taking confounders into play, and there was basically some confounders saying basically different customer segments. So there were segments that were per se more critical. Yeah? They have a lower rating, they are 1 point lower because they are so critical. Yeah, but if you look per segment, the more NPS, the lower the churn. Yeah, you see, you get causally true insights only if you have in the model the confounder, and the confounder is defined that he influences the cause and the outcome at the same time. Yeah? The confounder is not someone who's just noising out the outcome. That's noise. That's not disturbing. Disturbing is something which influences the cause and the outcome at the same time. That's called confounder. Right? And there are basically two merits to that. One is building larger models, including information which may be even an indicator for a confounder. The second merit is try to find patterns. If you basically cannot put those confounders in because you haven't measured them, you can still try to find some patterns in that. So typically, if your data within your framework clusters, there's a reason for this cluster, right? And the reason is a variable which you have not in the model. So you can kind of find those clusters, find the vector of it, use this vector information as a next variable into the model. There are different techniques around that. But again, the most important thing is start here. Yeah? Confounders are typically also here personal properties or situations. And of course you need a method which can handle that. Yeah? If you take conventional statistics, structural equation modeling, yeah, they just want to have metric variables. So how can you include the age or some other binary things in there? It's not allowed. And so these methods are of limited use. But with causal machine learning, we can now do that. And now it becomes helpful. And although we are not including so much prior knowledge, it turns out to be more causal, because it really can use and encompass the confounder. Yeah. Also, if you think in science, typically you build those small models because that's only where you have a theory for. But what actually happens is you leave all those confounders, making this increasing the risk very much that your findings are totally driven by confounders and you don't really know what you're measuring. Two examples that this is not theory but repractice. Again, a holistic data set on why people buy a beer brand. And what you find is, okay, yeah, because they think it tastes good. But behind that, what does it mean it tastes good is actually it's refreshing. And yeah, so you by building those networks, it condenses you an information, yeah, because you have a large network, you encompass the confounders, and you find here that it's refreshing, and it's especially me as a German was a highlight, because all German beers are promoted as tradition and good taste and good quality, but actually it turns out that's not at all what drives customer decisions. A beer is basically a refreshment drinks for adults. And if you look how advertising in the US looks like, it's exactly that. It's ice cold, refreshing, and so forth. It turns out you find that. A second example in skin cleansing. Yeah, of course you find the brand. It should be kind of enjoyable. It's lathering your skin, but the key driver of that you are really finding a brand good is a fragrance. That's a key thing. And if you look at the aisles of grocery stores, you see people the smell on it, because it's the only thing you really can witness, the smell, right? And also after showering, the smell is a key thing to buy, and you can really find that out of hundreds of variables and distill it down to insight, and that's what's really interesting. So that's why confounders, the master of puppets, it's important to. So last thing is we should model the reality as it is, and the reality is like that. It's like this tree. Yeah, what's the success drivers of the tree? It needs water, it needs sun, right? But in conventional statistics, we assume they are independent. Yeah, if sun is too expensive, you just put more water in it, it will die, right? You need water and sun at the same time. Typically, it depends on each other. It's called an interaction. Or there's an optimum of sun and optimum of water. It's called a nonlinearity. And actually, this is how reality more or less always looks like. But the thing is that you get a new plant, and you don't know what kind of success drivers, what kind of nonlinearities they have. So we need something which helps to find out. And machine learning can help. This is conventional statistic. You have a formula, you just fit it to the data and find the parameters, which is the steepness. But with machine learning, you are more flexible. Yeah, you find the data, the formula in the data. You find the nonlinearities. You find the interactions with that. Only thing you need to really care about is to not just use machine learning models, but you need to make it explainable. But explainable is not enough, as we have seen. You need to make it causally true. That's why you need to use those algorithms I mentioned, like automatic relevance detection. An example, this is kind of a marketing mix model for selling pharmaceuticals. One thing which popped out to be important is providing samples to physicians. Again, something pops out, a strange nonlinearity, and it turns out to be very, very reasonable, because if you provide samples, it's good, right? So it provokes the product. But if you provide too much samples, the physicians, they do not prescribe anymore. They give the samples away. So it's substitute sales. That's what you find in the data, and that's helpful when you really get those insights you haven't thought about upfront. Another thing is that in 5% of product launches survive, right, after 2 years. And I want to show you a result of a study where, using causal AI, we can change the whole outcome. Yeah? Conventional statistics had an R-square of 0. They didn't know why. And with causal AI, we could say with 81% which product would survive. And why is it? It's again a holistic model, but basically the red thing here is an important thing. We found that all those things which are important, they need to be managed well, all at the same time. Yeah. So you need to have a distribution, otherwise you're gonna sell, right? You need to have a good product. If it's bad, people don't come back, right? You need to have some mental availability of the brand. You need to have some good impression. You need to have some good price. So if you are managing one of them not good enough, everything falls flat, right? It's not additive. The world is not that way. It's like with your tree. It needs both, right? That's simply what the machine learning model found. So accept and master unknown complexity. And I'd like to close with the question, how do we sell internally causal AI? Because you may now love the concept of causal AI, but you may think, they will not believe me. And there are basically just going there and say, hey, you find the why, you now find the causal reason. That's not enough. I've tried that for 15 years. So that's not what you really need to do, is to find a pain point you can solve with that. Here are the 4 pain points I can see as an entry point. One is model drift. Yeah? If your business has model drift, you can say, hey, we have causal AI, let's solve it with that. Another one is when you have an issue with fairness in your model. You can again come in with causal AI. Or if your actions don't work, yeah, you recommend action, but suddenly it doesn't work, maybe you didn't find a causal reason for the success. And lastly, that if you see that, and that's what I see very often, a frustration that we have so much data, everywhere we have data, and we put it in the dashboards, but there's still a frustration and scarcity of compelling insights. And that's the first point, fourth point, where you come in. And next time, when I come back, I will tell you how to also use causal AI to actually tame generative AI. I have an example here, but my time is up.
Right. Good. Thanks a big hand. So before we break apart into the next round, which will be in different rooms, as you see on the program, there's time for some small questions to Frank, because it is a thought-provoking idea. You mentioned a lot of different techniques, so I can imagine that there is some questions from the room. Or your talk was very clear, Frank. It could also be the case. Are there no questions? Yes, there is. Hans.
Yeah, one question. Thanks for the excellent talk, by the way. Really liked it a lot. It all also made me think about when I started my career as a qualitative researcher. Basically, I think through good qualitative research, in-depth interviews, etc., you can also generate a lot of the insights that you highlighted here. What's your opinion about it?
My opinion is qualitative insight is very important to build those holistic models, to know which data to use and whether or not it finds the right thing. I know that might be true, but basically there is no mechanism to prove the validity of your claim. It's just your impression, right? But this causal AI quantitative framework has a mechanism to prove that it's correct. So I think it goes hand in hand. Insight generation is a process which starts with qual, right? And if you want to quantify and prove it more, you need to go into qual. And actually, causal AI as a explorative technique sits between qual and thing we know as a quant modeling, which is conformative research. But basically, this is also exploring like qual, but with data. So it sits in the middle. It bridges a gap which we have today.
Right. Any other questions? Yeah.
Thank you so much for your talk. I just wanted to ask something about structural equation modeling. In your experience, do you think it's possible to integrate or somehow utilize findings from machine learning while doing some sort of structural equation modeling?
Yeah. So structural equation modeling is good for validating hypotheses theories, right? And if you can get insights and then condense it into a machine learning model, and you can model nonlinearities if you know them. You can model interactions if you know them. Then you can do that. There are of course some computational limits because those models break down if you have some dozens of variables. So you really need to be sure, okay, you have all confounding things in here, and then you can even have higher accuracy. But to get there, you need first to do causal AI machine learning to understand how the world, as holistically, in a holistic sense, looks like. That's mine. It's basically this kind of research process. At the end, there is conformative research with structural equation modeling. But to get there, we have a gap which we don't look at today, which is more practical to my understanding.
Yeah, so I had also one question. So you gave us a number of examples where people were put on the wrong foot because they didn't include, let's say, confounders, for example. But how do you know that confounders are missing? So when do you start the process of looking for confounders and when do you stop?
Yeah, it depends where you are, if you're in academia or on a practical side. So yeah, you do what you can, right? So it starts, for instance, with qualitative research. But if you basically, in reality, it's like, hey, in 2 months we need to have a decision. So now you do everything to foster this decision. So do I have time to have qualitative research? No. So I ask some experts. Do I have time to measure, get new data? No. I just use the things I have. So it's actually never to find the ultimate truth because that's an unreceivable goal. It's to make the best decision we can make in this time.
Okay. Well, thank you for this excellent talk, Frank. And I have here some presents to thank you for, so give him a big hand.